Welcome to geometry. We want to begin looking at the second unit of our course, or the second part of the course, which begins with section 9 for us, which is all about axiomatic systems, or the axiomatic method, rather. So we talked previously about points and lines and that these are undefined terms. And we want to talk about this a little bit more generically in this section to give an idea of how essentially all areas of mathematics are developed, formally anyway. So the axiomatic method is, again, it's the foundation of all modern mathematics, right? It's where everything begins. So we always start off with a collection of undefined terms. Like we did with point and line. The terms are not explained in any way, just left with no definition. Okay, a lot of times we have experience with a particular area of mathematics, and so we have an understanding, right? We have a usual interpretation of what these things are, but formally they're undefined. So we take these undefined terms and we learn things, observe things, develop things, and these things we give precise definitions in terms of the undefined terms. So then a collection of statements called axioms are introduced without proof and assumed to be true. Okay, so we just make a collection of statements and we assume that these statements are true. Now, there's actually quite a bit of discussion that can be had about this. For example, the axiom of choice for the real numbers is a particular axiom of interest because there's a lot of mathematics that hinges on this axiom of choice. An axiom that we can talk about later, but there are some people that aren't entirely convinced that it's true, in which case significant amounts of mathematics would just be wrong if it were not true. So that's interesting. And then all other statements about the system beyond the axioms are called proofs. Or sorry, not proofs. They're theorems, which we prove. Theorems. Which we prove as consequences of the axioms or as results of other theorems, which are consequences of the axioms. So we see this development in each area of mathematics. So an example of this would be the natural numbers. These are numbers that we're super familiar with and seem extremely natural to us. Now, they're also called the counting numbers because if I wanted to count how many pens that I have, you might be able to see here in my hand, I've got 1, 2, 3 pens in my hand. Well, if I had no pens in my hand, then there is nothing to count, so there's nothing there. So the natural numbers are the counting numbers. These things make sense to us. So we know a lot about them, but we don't understand them at their most fundamental level, right? They weren't developed for us using axioms. And there are a set of axioms, and I have no idea how to pronounce this person's name, but I suspect it's Pino, named after, again, don't know how to say it, Gisop Pino. So these axioms are the Pino axioms, named after Gisop Pino, a 19th century mathematician. So these are some of the axioms. The first one, that 1 is a natural number. Okay, cool. Equals is a relation on the natural numbers that is reflexive, symmetric, and transitive. These things we are familiar with. Closed is a nice addition to what we know about relations, right? This is the equal sign is an equivalence relation, is what we're looking for here. All right, there is a function called S from the natural numbers to the natural numbers called the successor function. And it has three properties. If a natural number is plugged into this function, what comes out is a natural number. That makes sense. That, after all, isn't that what this notation says? For all natural numbers, the evaluation of that is not equal to 1. And then if the two of them, if two natural numbers are equal, sorry, if they're both in there and the evaluation is equal, right, two natural numbers, evaluation is equal, then those two things must be equal. So this is saying that it is 1 to 1. Right? It is a 1-to-1 function. Now, I suppose technically there are many ways that this could be done. Entirely possible. Let's see. But what would that function look like? One example of that could be, oh, not f, we're calling it s here. S of n is equal to n plus 1. Okay, this guarantees that everything plugged in is going to be greater than 1. And what comes out, of course, is a natural number. None of them are equal to 1. And this is a 1-to-1 function. Another example of this would be 2n. So that's interesting. So there is a function that looks like this. These are things that we're familiar with because we know what the natural numbers are. Okay, we know what they are. But without that, without knowing already what they are, it seems a little bit less obvious that these things could be considered S. All right. So another axiom for any set A, if 1 is in A, and if n is in A, then Sn is in A, then n must be a subset of A. Okay. Frankly, I'm not even quite sure what this is really trying to say. This is a bit interesting, right? Maybe pause for a moment and think about it. Okay, if n is in A, then Sn is in A. N must be a subset of A. I suppose I'll have to continue to ponder this. But the point is, it's explained. It's explained for us. Of course. This is the fundamental idea, right? This is the principle of mathematical induction. Awesome, right? Yes, of course. Oh, yes, I recognize it now. I recognize this. Yes, this is the principle of mathematical induction. There are additional axioms that introduce operations such as addition and multiplication. Awesome. But the point is that we're familiar with the natural numbers, but we're not familiar with all of these axioms. So even the things that we are familiar with do have the underlying axioms and theorems that can be proven based on those axioms. All right, so that's where we want to begin with this section. This is the idea, the basic idea of how modern mathematics is developed. All right. In the next video, we'll take a very brief look at the activity that's on the following page, which discusses finite geometries. An activity that you will need binder clips for. I don't think I have any sitting here right next to me, but you'll want some binder clips and some string. And if you don't have either of those things, feel free to let me know and I can get a hold of some for you. I'll see you guys again here shortly.